Okay, so 11.2, we are doing inferences about two means. And what's important here is we have dependent samples, so they're related more than the other section we're going to do later on. So they're matched. We've talked about independent versus dependent. In this case, they're matched in some way. A lot of times it's the same person's data before something happens or after. Or the example we're going to look at today in class is it's the same person, but they're doing an experiment. For one, they use their dominant hand. For the other part, they use their non-dominant hand, and they compare the results. So it's comparing something related. So the experiment they do in the example is kind of interesting. I don't think I have a way to do it in here though. Okay. So our null hypothesis for any type of test we're doing is the mean difference is equal to the population difference. So our mu sub d is going to be like our sample data. It's what we calculate based on what we're looking at. So there's no difference. Okay, a two-tailed version. This is just our alternative hypothesis is as expected. Left, oh, shoot. That is a one-tailed test, excuse me. It's been a morning. So our two-tailed test is just the means aren't equal. One is bigger, we don't specify which one. Left-tailed test, we're saying our sample is going to be smaller than the population. So smaller than than was previously stated. And then a right-tailed, let's go this way. Our mean difference is greater than our mean not. So honestly, they talk about left-tailed or two-tailed versus one-tailed test. For most of these, I don't know why I would do a one-tailed test. For a left or right tail, you have your percent of like your space is either in the you get more space in the left versus right tail than you would a two-tailed. So if you have an inkling it's going to go one way or the other, a left or right tailed is the way to go. I cannot think of a case where I would do a two-tailed over that. And just as before, two-tailed, we're looking there, a left and right-tailed is, oof, this is bad. I've drawn this so many times. So for all of these, if we reject the null hypothesis, it means we're in the blue zone as appropriate. So for the different things, that when we reject, we're saying there is a difference or we found a difference. So we reject the statement that there's no difference. Okay. What's interesting about this test versus pretty much any of the others we've dealt with is our mean difference, or D bar, which we're going to look at, can be negative. Because if you're comparing thing one to thing two, maybe thing one's bigger than thing two and you subtracting it a positive. Or maybe it's the other way, you subtracting it a negative. So you can have negative numbers for our D, which I think is interesting. Okay, reminder of an equation we're going to need, standard deviation. We've done this before, so I'm not going to spend really time with this thing. We've had a lot of equations in this course, so it's nice to remember what they are. Honestly, I had to look this one up too because there's so many standard deviation equations, I forgot which one I needed to use. So that's the equation. I know I said we were done with the nasty ones and this one's coming back. Sorry, it happens sometimes. Occasionally I'm wrong. It shouldn't be too big a deal. We should be able to get these pretty easy. All right. So don't forget that guy. Our test statistic should be whatever. A V bar is our mean difference. So you subtract your data values and then find the mean at the end. We will go through all steps on a problem to see how this works because it's not hard, it's just a little weird. Our S sub D is the standard deviation. That form is needed. Hopefully they give it to us in the homework, but they don't always. And degrees of freedom, n minus 1. Okay. So instead of writing out the example, I have the slide I'm going to pull up because I think it's interesting. If I can find it. All right. So we have a professor here who's measuring the time in seconds required to catch a falling meter stick for 12 randomly selected students, dominant hand versus non-dominant. So holding out hands one at a time, you have the stick, and how long does it take to catch it? Like, time, how long your reaction time. And you do dominant versus non-dominant because the theory is your dominant hand would be quicker than your non-dominant. That would be my theory. That's what they said. They do a coin flip to decide if you're gonna do dominant versus non-dominant hand first. Because honestly, once you practice one, the second one should be a little easier. I would think. And then they're gonna conduct the test at alpha of 0.05. So here is our data, and my silly self did not write these down. All right, let me scribble my data values real quick. So listed first is our dominant hand. And as I write these, note which one's higher. And is that what you expect for most of these? I'm going to pause my video so everybody doesn't hear me. Okay. I went and typed all of these in my Google Doc or my Google Sheets. Oof, not quite that big. So we can see them a little easier and we don't have to do this all by hand. Okay. My data is here. We have this. First thing we're gonna do is find the difference. So we're comparing the dominant versus non-dominant, right? Is that the order they put these in? I feel like that's off. Oh, yeah, no, that makes sense. The dominant should be smaller. Wow. Okay, so what I'm gonna do is take this cell, oh, whoops, equals this cell minus, not that, minus this cell. And yes, please autofill. And here's gonna be my sum equals sum. Hold these so I can find them. Important thing we need is our difference here for now. So add up all of my differences, I get negative 1.58. I'm gonna bring that over here. No, I think I grabbed the wrong standard deviation. So, D bar equals negative 0.158 over 12 because we have 12 students in this set. And what does that give me? Negative 0.158 divided by 12. I get negative 0.0132. Oh, I see what I did. Okay. I'm going to cheat really quick. Standard deviation is 0.0164. We can talk about how to get that later, but I'm stealing that off of my page. You're not going to do standard deviation on your X and Y column. You do that on the difference column, which is where I goofed when I was doing my thing. So T value is negative 0.0132 divided by my standard deviation 0.0164 over the square root of the number of things, in this case, people in my population. So negative 0.0132 divided by 0.016. Wow. I get negative 2.788. So that's my t-value. So mu is my population, D is my difference, so D bar. So for my null hypothesis, I say D equals 0. For my alternative hypothesis, we're looking at a left-tailed test. We're going to say our mean difference is less than 0 in this case. And it is, but is it big enough difference? Here's my T of 0. And the T I get is negative 2.788. Now we're going to go to the T table. We've been there so many times before. Our alpha level was 0.05. And our degrees of freedom is 12 minus 1, which equals 11. So we use that in the table to look it up. I'm just going to pretend we did that. And I get my T-crit is, when we look it up, we're probably going to get the positive of this, but we're going to call it negative because it's a left-tailed test. 1.96. Seven, six, five. Okay, so if I use my graph, I graph my T critical first, or I should have, I didn't, but and then I shade everything to the left. If we're in that blue zone, we're happy. That means we have a significant difference here. So we're in the blue, so we're going to say we reject null hypothesis. Evidence that the dominant hand, that the reaction of the dominant hand. A, C, D. Less than that of your non-dominant hand. So yay, we found a difference. That's what our hope always is, that we find some sort of difference. Okay. If we want to do the p-value test, we look for our t-value. Your 2.788, and that'll get you to the p-value you want. And you want your p-value to be less than 0.05, and it will be. We're, according to what I looked up, it's between 0.005 and 0.01. So either way, we're pretty good. The last piece of this, we've dealt with these before, but we haven't in a little bit, is a confidence interval. So what our confidence interval is, we take our data, we make an interval, and we say we're pretty sure, we're 95% confident our real data value is going to be within this interval. So that's kind of like you hear the political polls of the standard within a margin of error. Same idea here. So our lower bound we get our difference minus your t of alpha over 2, so you look that up, times your standard deviation over root n. Your upper bound is our d bar plus t alpha over 2 times standard deviation over root n. So it's nice that it's honestly like the same equation, but one's plus, one's minus. A thing to note for us, since our d is negative, Our lower bound is going to look like it's like we're going extra negative. So it's going to be smaller, but it's going to look weird. It happens. All right, so looking at our previous data, we had D bar was negative 0.0132. T alpha over 2, I'm going to cheat and just give you that. 2 point, excuse me, 201. And I do believe that was negative. Yeah. And our standard deviation will always be positive. And our N was 12. For our lower bound, plug our data in, 0.0132. No, it should be positive. Sorry, it is the positive of this. If not, it's not going to make sense for us. Okay. 2.201 times 0.0164 over 12. This is a calculator problem, so negative 0.0132 minus 2.201 times 0.0164 divided by root 12. Oh, good. So I get, this is going to equal negative 0.0236. For upper bound, we change one thing and just say plus. Which is why I was trying to copy paste it. All right. So we get two fairly small numbers. They're really close to 0, but they're not 0. So we can say we are 95% confident that the mean difference between reaction times is between negative 0.0236 seconds and negative 0.0028 seconds. Because this interval doesn't contain 0, the evidence suggests that the reaction time is different. So as long as our confidence interval doesn't contain zero, we're fairly certain there's going to be a difference. In that case, it's a really small difference, but that's okay. It's still a difference. All of our values were really small anyway, so a small difference makes sense. If it contains zero and you think your real time is in that interval, your real time could very easily be zero. So that's a case where you think there's no evidence for a difference. But as long as it doesn't, you're good. Okay. I'm going to stop my video and then chat about what we're going to do at the end.